So hello everyone to the last day of DevConf. Good morning. Our first speaker is Hannes, and he will tell us how to do performance analysis using the perf tool.
Good morning. Can you hear me? Okay, it seems to work. Yeah, as is the echo okay? Okay, I will leave it like that. Yeah, we are often analyzing the networking stack and are also looking into a lot of performance issues, also trying to reason about bugs and new code paths we are trying to add into the kernel. We often use a perf framework or the perf kernel subsystem for that. And it allows us to do a lot of things, and I want to present some things I am used to in my daily life nowadays with perf. So if we look at performance issues in the kernel, we can basically see different areas where we try to optimize the kernel. One is like algorithmic complexity, where we try to improve the algorithms we use in the kernel to just spend less time on particular lookups or to make particular decisions in the networking stack. We have memory access behavior, which is basically getting more and more important when we add more CPUs and build up higher NUMA systems, and the interconnects between more and more CPUs are not fully meshed anymore, so we even have to cross multiple CPUs if we want to fetch a part of memory from another CPU. We build up quite a lot of assumption in the networking stack, how network packets are received on the interfaces. So there's lots of fast paths and slow paths today. We have kind of caching of, for example, routing lookups, and that also only helps if the caches are not evicted on every packet which is across the cache. And then there are some things which are not that important, but basically sometimes it really should also be looked at as raw instruction throughput. That's basically only important if you look at crypto or if you look at hashing patterns we use or hashing functions we use in the kernel. So I want to focus on at algorithmic complexity. Basically, algorithmic complexity is quite easy to find in the kernel. So normally what you can do is that you can try kind of different workloads or benchmarks. And even if you use the normal perf cycles counter, which is basically the default, if you just use perf, it will basically show up near to the top of your profile report. If you want to improve on that, there's this, what you can use as an event in perf top -e is a cycles KPP. So K is for you are only interested in kernel code, so it filters out user space code. And PP are options that allow you to actually improve the precision how it is sampled. AMD and Intel added two different subsystems for that in their CPUs. Intel is the PEPS, precise event-based sampling, and AMD is instruction-based sampling, where they allow you to better pinpoint which instructions are actually which instructions actually cause the stalls in the CPU pipelines, for example. So, for example, you have multiple atomic instructions, and the first instruction is executed asynchronously, and you actually hang on the second instruction. That might be a completely different subsystem, and they don't have any relation to each other, but actually, hopefully, the latency should show up on the first atomic instruction because it's actually causing it. And so those two frameworks improve the precise level, and I normally use them always nowadays. And the built-in perf tools normally also enable the more precise accounting in cycles. Otherwise, you will see a lot of other perf examples in the next slide, so I guess it's just okay. And you can, if the algorithm is mostly big, you can try to add further trace points, like I will show you on the next slides, into your set, and then analyze the performance with that. But otherwise, normally you have to read the source code and you have to analyze it, and maybe, or most of the time, have to in some kind rewrite it, like for example Alex did with the fib tree stuff, which gave a quite huge performance improvement. If you are too lazy and don't want to improve the code, you can try to come up with something like caching or doing fast pass for some rather complex, or fast pass for some simple stuff and leave the complex pass falling down to the slow algorithms. Okay, memory access behavior is a bit easier to actually analyze. We currently face basically two problems, which I said before, is parallelism actually has some problems that we fetch memory from remote CPUs. We also run into some problems with lock contention nowadays. And yeah, so one example is where I didn't actually thought about that such a patch would improve performance was Eric Dumazet's MLX4. MLX4 is Mellanox driver for Ethernet 10 gigabit improvements, where he just, in a large function, he split out all the cache accesses to some specific memory. And by using access 1, which is in the kernel just a wrapper for volatile. So volatile in the kernel means that basically the compiler is only allowed to touch the memory location in case for reading or for writing when you say so. So it's not, for example, allowed to spill out the value back into the location or read again from that location. And with volatile casts, you can force the compiler to really only do the memory touches only if you specify them. So by just moving code around and fetching ring cons, which will get added here later on again, he can improve the access to cache lines in such a way that it speeds up by, I guess a patch did an improvement of about 50%, so it was quite a large patch, and it was also a huge performance benefit. And the problem, what happens before, is that the compiler saw that ring cons is incremented by txbbs skipped, and the compiler generated a read modify write expression, which forced the memory line to be exclusive on this node, and so it got more complicated for the CPUs to actually track that. So compilers normally do not tend to optimize memory access patterns in large functions, so we normally have to do that ourselves. And access once is actually one nice feature the compilers have, because we can specify when memory is accessed. And otherwise the compiler normally tends to just lazily try to read the pattern, and that might cause some kind of storm to the memory bus. Yes, as I said, it's also important to avoid read modify write instructions, or at least try to avoid them whenever you can. So often you also see if kernel patches which improve performance, which are kind of just reordering the members of a structure. So the reason for that is that basically current CPUs only deal with cache lines. So they always fetch one full cache line and they always write one full cache line. There were some extensions in the latest CPUs nowadays that it's not that horrible anymore. But still, if you can avoid to touch cache lines, you should try that. So for example, if you have some piece of code and it only tends to write to about a few bytes, you should try to group those few bytes in your C structure so that it is on one cache line and that the CPU does not spill over multiple cache lines. There's one rule that the most common used memory or members should be at the top of a C structure. That's basically not that correct. You should try to at least put them at the beginning of a cache line all the time, so they should be cache line aligned. But as I said, current CPUs added some extensions. So one is early restart. Early restart actually allows the CPU to proceed with instruction processing as soon as it receives the word for which the CPU is currently blocking. So the memory unit fetches one complete cache line, and normally the instruction pipeline waits until the complete cache line arrived. And early restart now allows that the that the pipeline starts to process the instructions at the time when the first word, which is actually critical, is received, but the full cache line is not yet in the CPU. And critical word first was added later on. That allows the CPU to actually pick a specific word in the cache line and not necessarily start with the beginning of the cache line. So those two CPU features tend to not make these optimizations that important anymore, but at all you should at least try to also optimize for older CPUs. So memory structure reordering is still a pattern what you should do still today, I guess. And even if you don't have Intel CPUs, I guess it's also the same on older CPUs, and they kind of not to have those fancy extensions available. Otherwise, if you want to look at perf already has a lot of hardware cache events where you can sample cache loads, cache misses in the specific caches. Yeah, I just wanted to give it as a hint. You can just perf record minus E. I hope you all saw the first presentation on how perf record works. So basically what you can do is perf list cache, and you will also see all the possible events you have in your CPU and enable them, or you can even enable all of them, and will give you some hints on where in the code your cache misses show up. It's actually pretty easy. EBS and PEPs actually allow you to see what memory locations caused the miss, but it's something I could not talk in the slides because there's also some problems with the implementation upstream for that. But nonetheless, there was a new tool added in perf recently, which is perf-mem record. Perf-mem record allows you to actually pinpoint specific code where the cache misses happens, and I try to know, just to demonstrate a bit of that. So, just very short. It allows you basically to, this was basically, I just tried to show you the history. I just did a perf-mem t-load record stress -c1, so I just wanted to have one CPU spinning on some data. I don't know what it really does. And it records all the loads from the CPU or from the memory, and the perf-mem report then looks like this. And you can see where packets or where your memory is hit. It's a bit bad to see if you don't have. Yeah. So you can see memory access patterns, basically seeing where you hit at one cache and where you didn't hit at one cache, and you can then perf annotate into the functions to see if you can somehow reorder your memory accesses, or maybe try to cache something per CPU. Yeah. So perf-mem record uses new syntax in perf events, which I guess is not documented yet. So there's this sys-devices CPU events path on every system or every CPU, and below that you also have CPU events which you can use in perf record. So this perf-mem record, they use CPU mem loads or CPU mem stores, and also those precision modifiers I talked about earlier. And I think you should try to explore what else is there in sys-devices CPU events, because it allows, for example, on AMD, you have something like an AMD Northbridge. You can also record the memory loads and stores to the PCI bridges and stuff like that. So you can check, for example, if your alignment to the PCI Express bus is correct and stuff like that. It's a bit of far away. And too much for this presentation. Hopefully I can do it in another one. Okay, assumptions on networking traffic. We added some fast paths in the kernel and some specific features which are problematic if they, or which only allow you to give full performance if they are actually hit. So for example, we have this xmit_more, which allows the kernel to finally achieve line rate speed, but it only really works in case you actually hit the feature and the kernel can aggregate multiple fragments and only issue one tail write to update or to send out the packets. We have different offloading strategies in the kernel, which also only work if the protocol is understood by the kernel and if, for example, TCP does not reorder packets that much. We have routing caches, which only work if you have connected sockets, of course, and don't change your routing cache, or your routing table is not changed every millisecond by some routing daemons. We have flow-sensitive packet steering, and of course, if the CPU does not correctly steer the packets to the CPUs, it also horribly breaks. And that's actually not that much into we try to, and yeah, those optimizations are in place, and it's now important that we sometimes, if we analyze performance, we just need to somehow adapt the traffic maybe, or adapt the code slightly, just that these features now become enabled for those kind of traffic. And I want to focus a bit on xmit_more. So if we try now to find out if our specific workload can work with xmit_more, we first try to install a filter with perf probe-f. So perf probe-f just tells us which possible functions are in the kernel. And of course, one needs to read the code a little bit, but the first command basically gives us a list of all functions which have def and xmit in them and shows it to us. And after that, so it's a bit short on time, so I guess I would just, I hope you can get the slides later on from the website and just try the commands yourself. So you will see a list of commands emitted. And after that, I will just print the lines of the functions, and it will tell us at which lines specifically I can probe. And the probing, so you will, for example, then see that there's, in my specific kernel, line 17 is a good place for adding a probe point. So I can now list this command, I can now see which variables I'm able to capture if I insert a probe at this point. So it tells me, for example, I have a variable called skb, I have a variable called def, which I use here, and I have a pointer to the next skb, which is called next, and I use it as an indication if xmit_more is indicated to the network interface. So this whole line basically does nothing like adding a probe point, which is called dhsx, which is just a shorthand for def hard start xmit. The probe point is inserted at line 17. I add another argument to the perf script via if name equals. So this is just a name I want to have and I want to process later on. And I say that I want to copy the name of the device, which is a string. So this is a type modifier, and it just assumes that basically wherever name points to is a string which is null terminated. We'll copy it out to user space and to the trace log, and I also copy the xmit_more equals next. So the next pointer, which is my indication if xmit_more is being set. And this is mostly a pointer, so if I don't specify any type, it will just get the type from the debug info information. And I just look at xmit_more like, is it 0 or is it non-zero? So there will be an actual pointer in it, but it doesn't. I don't care about that. So and after that, you can just perf record. I just added this as a shorthand. You can normally just use this dhsx here. I just always use star for enable all trace points. Can run your workload, and after that, you will just see. And I guess it's in the next slide or in the next slide after that, you will just see a list of where and when the trace points are hit. So it's quite easy to monitor if a specific workload actually hits xmit_more, for example. Some other small things you should make notice. If you have modules, you sometimes have to add your debug info module path into the perf, otherwise it's just the same. Here I check if xmit_more is used via the IEEE wireless LAN interfaces. There are some other things you can easily do. For example, if you just want to see which return values defacto start x mid emits, you can also place a probe at the return, in the return statement, and just copy the RAX register, which is easily available via this readwile value to user space. And by the way, if you do that for user space, you can always on Fedora, I don't know about Debian, I guess you have to install those -dbg packets. Always install the debug info packets, and then you can just -x and use the user space binary, and you have basically the same feature set as in the kernel. So if you try to use that, you will very, very fast see some problems because of compiler optimizations and inlining. And there are some tips I can give you. So the kernel has a no inline defined, which you can use to force the compiler to not inline functions. So you have to recompile your kernel, but sometimes it's worth it because you want to trace quite a lot. So you specify a specific function as no inline, and after that it should show up in your KR or sims and should also be traceable. If it's in a header, you kind of have to rearrange the header maybe a bit, or just have to create a new function, an object file which only calls this function, the inline function, but is no inline specified. Sometimes you have to fiddle a bit with export symbol because you have multiple definitions of it and stuff like that. But normally you can, with no inline, it always helps that you can get a pur and find trace point. In some cases, debug info doesn't work correctly, and you cannot see variables cannot be accessed because they did not trace correctly through the registers. So always looking at the source code or in the assembly in GDB does also help. So for example, if you get something like that and you actually saw that you can trace all those, for example, if I remember correctly, the more flag was the problematic one. So it could not track that. And it tells you that basically there's no address for this more flag, so I cannot insert the trace point. You can try to understand the assembly and then just, for example, use manually specify some way how you could work around it. For example, if you see that it is in a register, you can just specify the register. You basically can copy all memory during a trace point to user space. So for example, here I'm adding an offset to the register and just copy that as an unsigned 16 to user space. In this example, DE is the same as SKB. So SKB is at the time in RDE, but you always don't specify the length of the register like R or E. So it's just the DE register. And yeah, basically you can specify everything. You can trace all and every memory location in the kernel during the trace point. There's also a -f-externs where you can see all globally available symbols where you can try to copy memory out during tracing. So what this gives us in the end, that I have received 4 packets on my wireless interface, and both of them got aggregated. So 2 packets got aggregated always in one packet, and then they were pushed into user space. Any questions about perf? Because now we are going into some other direction. Okay. So raw instruction throughput is the next topic I want to show for a short time. Normally does not give that much of a performance boost in the kernel, but sometimes it does, like for example, very often called code or crypto or hashing, where you have tight loops which execute over the memory all over very often. And then you should try to optimize the code path a bit. And sometimes that's not actually possible for you to decide how it is optimized, because the compilers do most optimization nowadays. But sometimes there are really things like for example, special CPU instructions, like I use, for example, CRC32 enhancements in the Intel CPUs in some of the following slides, where it is actually very much, where it gives a huge performance boost if you try to be architecture dependent. And but nowadays, as showed earlier, mostly you have memory access stalls and stuff like that. So raw instruction throughput is not that important. I would actually try to open misoptimization bugs in GCC Bugzilla if you see something miscompiling, and I would not like to see code added to the kernel which does work around that by using inline assembly, but sometimes it does not work otherwise. Also, if you try to add big chunks of code just in assembly to, for example, always have a fill pipeline, it hits the L1 cache, the instruction cache, and the instruction cache also then has to decide which code is more hot and often does or has a problem that it spits out the wrong code after that. So it's always some kind, you have to balance between code size or multiple code implementations for specific paths and reaction on the whole system. Yeah, and if you try to do that in assembly, always try to specify or also program a build constant p wrapper. So basically, in case you push constant values to the compiler, it can eliminate the whole implementation and does not need to run the assembly code, because GCC can, of course, not optimize assembly code and only can see or can constant fault what is written in plain C. But there's one great tool out there I just want to present with the Intel Architecture Code Analyzer. I use it nowadays for looking into how instruction throughput can be optimized. Basically, it does not run the program, but just inspects what is between two markers. So this is the begin marker you have to include somehow in your binary, in your machine code, and that's the end marker. And basically, every instruction which is between them will get analyzed by this architecture code analyzer. And you have mostly two modes. One mode is the throughput mode, where it tells you which port in the CPU is pending and which is executing which instructions at that time. For example, this is the CRC example. It tells me that I have 18 cycles, it needs 18 cycles, and I have a throughput bottleneck on port 1. And it gives you a lot more information, but I'm a bit short on time. So basically it tells you how long each port is stalled, and for example, which instructions get fused into one instruction. And so you can just try, for example, to reshuffle the assembly code a little bit, that you have less micro-ops instructions, or so you can, for example, reduce the pressure on port 1. Same is possible with latency mode, so you can analyze latency in your assembly code and check where you could, for example, improve latency. This example is also pretty much optimized already. The critical path does not in any way, so ports do not have any kind of dependency in here, so this port is only used for one tick, and then the other port is used, so it's optimized pretty much already. It gives a lot of more output, and you just have to read through it. It's basically self-describing and self-explaining. It can also generate a lot of cool graphs where you can see which initial instruction has a dependency on all the other instructions, and you also can try to analyze and come up with a better implementation if you, for example, see any specific loads from memory which depend on other loads where actually no dependency maybe is required. So splitting up loops again, or trying to basically get dependent code out of loops. You should see that easily in that. Okay, I'm finished now, and I hope there are a lot of questions.
Can you go back one slide and
Yes.
what's in the pink and the green?
Pardon?
What are the different things in the green and the pink? It's hard to read from.
The red one, this is basically the CRC32 instructions, and those are the instructions which are in the other, which are the critical path. So the CP is a critical path. It's basically what defines the longest path through the whole chain, and that's basically the red boxes in there. And you can see that, that the load instructions, which are the green ones, have dependencies on the CRC instructions. So those must be finished before those other one can actually be executed. Any other questions? Yeah?
Is this tool free to download?
Yeah, it's binary free. So it works on all, if you just Google for Intel architecture code analysis, you will find a download link and you can use it on all platforms. And normally you just use a header which you include, and it has a compatibility wrapper for all major compilers, which allow you to just include those bytes in C or in assembly, and you just recompile it and run the tool over your object files. That's basically how it works, and it's not much of a problem. Yeah.
So you have like 10 minutes, I think. Can you go back to the code analyzer and explain what these ports are and what this table really means?
Yeah.
I'm completely lost.
So every port has specific meanings in a CPU. So for example, you have very generic ports, and for example, this 0 port is also a port which can do the division instruction and stuff like that is actually depending on the contents of the registers, so it's not implemented in the tool. So if you, for example, have code and you do divisions in it, it will bail out and tell you that there's a problem in the implementation. And otherwise, basically, those ports are just the execution ports of a CPU. So they do the execution of specific things. And so, for example, here you can see that basically every port is able to do anything, and the CPU just shows you where the instructions are scheduled to which port, and how long it does need, how long the port is busy, and that's basically it. So you just see that that 2 ports are for this instruction. There are 2 ports busy, but they don't overlap because you see that basically the time window is quite short. So it does not overlap. If you have, for example, a 2 or 3, so it would use a port for 2 or 3 cycles. And if you would have an instruction after that which also requires a port, you would have a resource conflict on that port. And so then the CPU must stall and must wait until the first instruction basically is already finished the processing. If you look at the output of the tool, it's basically very much self-describing because it actually shows you, for example, that those flags is micro-op fusion. So it does kind of fuse those instructions together in the CPU. And it also gives you tables if you have specific kind of port if you have resource conflicts on your ports, it does actually print you the resource conflicts and also tells you how you can maybe improve that a bit. So the full output is actually not that hard to read.
So is static analysis on the object code?
It's only static analysis on the object code, so it cannot follow loops that much, and basically just runs through the code and gives you one flat interpretation of it.
So in case of things like branch prediction misses and such stuff, this
no, you cannot. Does not really make sense. So for branch prediction, there's actually now there are branch prediction tracers in perf, which require also the recent CPUs, and you can use that, for example, to actually pinpoint if your branch prediction is working correctly in some cases. Any other questions?
So what are some of the big bottlenecks you have found with using the perf tool? Or what have you been able to solve so far? Any examples?
So nowadays I mostly use it for verifying that my patches are working, or for example that patches submitted to NetDev are correct by just, for example, checking that specific functions are called in a correct way by tracing the arguments. In terms of XMIT-more, for example, we use it to verify XMIT-more behavior on some of the of some of the network cards, and we also used it, for example, I use it, for example, to check how GAO is actually working on some network cards or on some traffic patterns, and if it could be improved in some way. But mostly I use it for verifying these days, and it's also very good for bug hunting. Any other questions? Okay then. Thanks for watching. Sorry. I just muted.
Can you hear me? Can you hear me? No?
No.
Can you hear me now?